Hello friends, this is Priyanka. Today we are going to solve a problem on given mechanism. In this video we are going to draw velocity diagram and acceleration diagram with some suitable scale. Now first I will read what is the given problem. In the mechanism as shown in diagram, the crank OA rotates at 20 rpm anticlockwise and gives motion to the sliding blocks B and D. The dimensions of the various links are OA 300 mm, AB 1200 mm, BC 450 mm and CD 450 mm. For the given configuration, determine velocities of sliding at B and D, angular velocity of CD, linear acceleration of D and angular acceleration of CD. So this was the given question. Now most important thing is that we have to draw space diagram with some suitable scale. Now if we observe the dimensions here, the crank OA is 300 mm, that means we can say 30 cm. So if we consider here scale, we will take 1:1/5. So this 30 cm we have to take 30 divided by 5, that is 6 cm. In the same way, this AB is equal to 1200 mm, that is 120 cm. So 120 divided by 5, that is equal to 24 cm. Then BC is equal to CD, which is equal to 450 mm, which is equal to 9 cm. Now we will take one horizontal line in the form of dash and dot, and on that line we will consider the center O. So this crank OA is inclined at 30° angle. So we will take here OA is equal to 6 cm as per the scale, and from that point A I will draw here one line and which is having length 24 cm. So here the initial point is A and final point is B. So at point B there is the slider, and what is the length of this link AB? That is 24 cm. So with the help of compass also we can select here A as a center, and in compass take the 24 cm distance and mark one arc, and the point of intersection with this horizontal line will be the point B. Now the BC, distance BC is given. So as per scale 9 cm we have to select here the point C, and CD is also 9 cm. But here one condition is given, that is the distance from this point O to this point D is given, that is 1050 mm. So we can say 105 cm. So as per scale we have to take here the horizontal distance in between this center and the direction of motion of the slider at point D. So this distance is 21 cm. So how to select that? So if I draw here one vertical line passing through this O, then from this line we have to draw another line with scale 21 cm distance. Now here this line we have to show in the form of dash and dot, because here within this line or along this line there is the motion of the slider at point D. So now we will again take the compass. So in the compass take the distance or scale which is equal to 9 cm, because the distance in between C and D is given 9 cm. So this horizontal vertical line is already getting selected at a distance of 21 cm, and from here mark here one arc. So the point of intersection will give us the point D, and at this point D draw a slider. Now if we observe this mechanism that is also given in the question, so here this slider at point B is having horizontal motion along a line which is passing through this point O, and the slider at point D is having vertical motion along this vertical line which is at a distance of 1050 mm from the vertical line passing through O. So in this way this diagram is getting completed. Now we will calculate what is the linear velocity for this crank OA. So for this the rotational speed is given, that is NAO, that is the N of this point A about center O, 20 rpm. So from that we can find out the angular velocity for this omega AO, that is 2 pi n by 60, which is equal to 2.1 radians per second. Now from that we can find out the linear velocity. So linear velocity of A with respect to O. So O is the fixed point. So we can say simply VA, which is equal to omega AO into OA, that is 2.1 into OA. So what is its length? So we have to take in meter, that is 0.3 meter, which is equal to 0.63 meter per second. So this is the linear velocity. So we know that the linear velocity is in the perpendicular direction to the link. So with the help of protractor we have to show this direction. So I will align one edge with this link OA, and from the other edge I will draw the perpendicular line. But in which direction we have to draw the line? So we know that the rotation is in the anti-clockwise direction. So in the same direction we will draw one line passing through this point A. So along this line there is the velocity of A with respect to O. Now we will move for the velocity diagram. So for that, if we observe point O is the fixed point, so I will consider one particular point as the point O. Now the direction is here, that is shown in the diagram with the help of red marker. So what is the scale that we have to take? So I will consider here scale 1 meter per second is equal to 20 centimeter. So as per this scale, what is the magnitude? That is 0.63 meter per second. So if I write here 0.63 meter per second, what is the scale? So here we have to take cross multiplication, that is 0.63 multiplied by 20. That is 12.6. So 12.6 centimeter we have to take one line and parallel to this VAD. So arrow is in the downward direction. So here from this point O I will take 12.6 centimeter line. So here is the point A and we have to show arrow in the same direction. So this vector OA indicates velocity of A with respect to O, or simply we can say VA. Now we will move for the next. Now from point A there is the link AB. So again we have to draw the linear velocity. So we know that the direction of velocity is perpendicular to the link. So I will draw here one line perpendicular to link AB. So this is the construction line. So parallel to this line I have to draw one line. But currently I don't know where is the direction of the velocity. So from both directions I will take here the line passing through this point A. So this is the line. So if we observe at the end point B there is the slider, and this slider is having horizontal motion which is along the line passing through point O. So how to show the motion of the slider in the velocity diagram? So we have to draw the same horizontal line but passing through point O in the velocity diagram. So I will draw here one horizontal line passing through this point O. And this point of intersection is nothing but the point B. So I will say this is the point B. So here initial point is A and final point is B. So I will show arrow in the upward direction. And this vector AB indicates velocity of B with respect to A. So I will say VBA. Now here the initial point is O and final point is B. And this vector OB indicates the velocity of slider B along this line, along this horizontal line. So simply we can say VB. Now we have to plot the point C, because here the point C is given on the link AB. So how to plot that? So now we can measure here the length of the link AB. So this length of the link AB is 10.5 centimeter. So now we will take the ratio. So in the space diagram we know the ratio BC divided by BA. So BC is given 450 millimeter, BA is given 1200 millimeter. And from this velocity diagram the distance between vector A and B is 10.5. So now only one unknown term term, that is BC. So from that we can calculate from the calculator. So BC is equal to 450 multiplied by 10.5 divided by 1200. That is 3.93. So BC is equal to 3.93 centimeter. So now I will take the distance from point B is 3.9 centimeter. So here is the point C. Now from this point C there is the CD. That is, here is the link CD is connected to point C. So how to measure how to indicate the velocity for this link CD? So again it is in the perpendicular direction to the link CD. So I will draw here one line which is the perpendicular to this link CD. So now from this point C I have to draw one line parallel to this construction line. So I will take here one construction line. So now I don't know where is the exact direction for this point C. So on both sides I will draw this line. Now we don't know where is the exact location of the point D. But here it is given that the D, that is at point D there is the slider, and the slider is having motion along the vertical line. So this motion along the vertical line is always the motion with respect to fixed point. So here is the fixed point O. So I will draw one vertical line passing through the point O. And here is the point of intersection, and this point of intersection is nothing but the point D. So remaining lines that we have to remove, and here we can say from this C to D, this vector indicates the velocity of D with respect to C, because here the initial point is C and final point is D. So I will say that here is V D C, and from this O to D it indicates velocity of D with respect to fixed point O. So for that I will simply say VD, because O is the fixed point, so not necessary to write the O. Now again we can also find out what is the velocity at point C with respect to fixed point. So for that we have to just join these points O towards C, because this point C on the link AB is having velocity with respect to fixed point. So I will join here O to C, and this vector O to C indicates us the velocity of C with respect to O. So simply we can say VC. So this is the velocity diagram. Now we will move to the calculation part. So here first we will calculate the velocity of B. So velocity of B, that is the slider at point P. So we have to measure the vector O to B, that indicates the velocity of slider B along this horizontal line. So what is the length of this vector OB? That is 9 centimeter. So with this scale 1 meter per second, that is equal to 20 centimeter. So if I write here the 9 centimeter, so here is the question mark. So again we will make here the cross multiplication. So 9 divided by 20, that is 0.45 meter per second. Then the next is velocity at this point D, that is the slider at the point D. So again we have to measure the length of this point D with this length O. So this vector O to D. So what is the length? That is 4.7 centimeter. So again with this scale it is 0.24 meter per second. Then again velocity for this D with respect to C. So for this velocity of D with respect to C means we have to measure this vector D to C. So its length is 8.5 centimeter. So with this scale 0.425 meter per second, that is the velocity. So now we will calculate the angular velocity omega CD, that is the angular velocity of this omega. So for that what is the formula? That is the linear velocity divided by the length of link. So if we observe velocity of D with respect to C, so we have calculated 0.425 divided by length of the link C to D. So it is in meter we have to take, so 0.45. So if we calculate this, we will get 0.94 rad per second. So this is the magnitude. So what about the direction? Now if we observe, here is the link CD, and in this velocity diagram for this link CD, the direction is given is towards the right hand side. So I will show the same direction in the space diagram. So along this construction line, this is the direction for velocity. So I will draw this line, and direction I will give the same direction. So I will say that this is the velocity of D with respect to C. That means here C is the center. So now if I take the C as a center and move the compass in the direction for this velocity, then here is the direction. So we can say that this direction is anti-clockwise. So how to write the answer? That is the anti-clockwise direction about C. So this is the answer. Now we will move for the acceleration diagram, but before that we will calculate the radial component of acceleration from the linear velocity. Now if we observe for the crank OA, the angular acceleration alpha is not given. So we will consider here the crank OA is rotating at the constant speed and the tangential component of acceleration is 0. So we will consider here only the radial component of acceleration, and this radial component which is the total acceleration of this point A about O. So how to calculate it? So we have to indicate in this way, that is A raised to R AO, which is equal to linear velocity square divided by the length of link. So what is the linear velocity? That is VA square by length of link OA. So here 0.63 square divided by 0.3, which is equal to 1.323 meter per second square. Now in the same way we will calculate the radial component for this link B to A. So here again linear velocity square divided by length of the link. So it's 0.525 square divided by 1.2, which is equal to 0.23 meter per second square. Now in the same way for the link C to D, we will again calculate the radial component. So for that again linear velocity square for this link C to D divided by length of the link. So here 0.425 square divided by 0.45, which is equal to 0.40 meter per second square. So these are the radial components, and with the help of these components we have to draw the acceleration diagram with some suitable scale. We will take here scale 1 meter per second square is equal to 20 centimeter for acceleration diagram. Now we know that the radial component of acceleration is in the parallel direction to the link. So first we will take the radial component of acceleration for this crank OA. So here no any tangential component, or we can say tangential component is 0. So I will use the black marker because this radial component of acceleration is equal to total acceleration. So now what is the direction that we have to take? So if we observe here, the direction is towards the center. So here O is the center. So I have to take the direction that is the downward direction. So first select the point or particular point as a O dash for the acceleration diagram, because this is the point O is the fixed point. Now I will draw one line parallel to this crank OA, but in the direction that is in the downward direction, and passing through this point O dash. So here if we draw one line, then what is the scale that is required to take? That is the important point. So here the magnitude is 1.323 meter per second square, and here we have taken scale 1 meter per second square is equal to 20 centimeters. So if we multiply 1.323 that is with 20, then we will get 26.46 centimeter. So here we will take 26.4 centimeter, and here is the final point. So initial point is O dash, and what is the final point? So final point is A dash, and here is the vector, that is I will show the direction, and it indicates the acceleration, or we can say total acceleration of A with respect to O. So simply we can say A to the base A. Now if we observe the diagram, here is the link AB that is connected with this point A dash. So how to draw? So again we will draw first the radial component of acceleration, because for this link AB, here is the, we have calculated what is the radial component of acceleration. So it is 0.23 meter per second square. So now what is the direction that we have to take? So if we observe for this link A to B, here A is the center because we have calculated the velocity of B with respect to A. So here is the velocity of B with respect to A, that is calculated. So A as a center. So we have to give the radial component direction towards the center. So this is the upward direction. So for radial component I will use the red marker, and what is the magnitude or what is the scale that we have to take. So for 0.23 meter per second square, as per this scale it is 4.6 centimeter. So now I will take the line parallel to this link AB. So it is difficult to take, so I will take, and we have to take the magnitude. So magnitude is equal to 4.6 centimeter. So this is the radial component. So from that we have to draw the tangential component also. So here I will say A dash to A double dash, and we have to show arrow also, and this vector A dash to A double dash indicates the radial component. So radial component of B to A. So I will say A raised to R, B to A. Now again we have to draw the tangential component. Now the exact location of B is not known. So tangential component is in the perpendicular direction to the link. So here this is the perpendicular direction that I have drawn, that is this is the construction line for the velocity diagram. So in this direction I will draw one line but passing through this A double dash. Now again I have to find out where is the exact location of B. So how to find out that? So if I observe, here is the B and there is the slider, and which is having reciprocating motion along the horizontal line which is passing through O. So in the acceleration diagram also, the reciprocating motion or sliding motion we have to show as it is. That is, we have to draw one horizontal line and passing through the O dash. So I will draw here one horizontal line. And this is the point of intersection, and this point of intersection is B dash. So here from A double dash to B dash, so this is the tangential component, and here we have to show arrow because this is the initial point, this is the final point. So I will say that this is the tangential component of BA, that is A raised to T BA. Now here initial point is O dash and final point is B dash. So what this indicates? So this indicates the acceleration of B with respect to O. So simply I will say AB. Now if I join the end points of this A dash and B dash, that is the radial component of acceleration and tangential component of acceleration, that is A dash and B dash, then I will get the total acceleration. So this is the total acceleration for the link AB. Now if we observe on this link AB, there is the point C. So we have to decide where is the exact location of this point C. So I will take ratio, that is AB divided by BC. So in this diagram, AB divided by BC, which is equal to, in this diagram we have to take A dash B dash divided by B dash C dash. So here we can measure this A dash B dash. It is 15.7 centimeter divided by B dash C dash. So here the unit is centimeter, so I will not taking. So now we have to write what is distance A, B and BC. So it is, we know that is 1200 divided by 450. This distance P dash C dash is 5.88 centimeter. So we have to plot here from B dash to C dash, that is 5.88 centimeter. So in this way this point C is getting located. Now if we observe the space diagram, from this point C there is the link CD. So for this link CD again we will draw here the radial component of acceleration. So here we have already calculated the radial component of acceleration, that is 0.40 meter per second square. And as per the scale, if we convert it, it is 8 centimeter scale that we have to take. Now which direction we have to take? So if we observe here, C is the center and here D at point D there is the slider which is having velocity. So we have to draw radial acceleration, that is the radial component of acceleration towards the center. So this is the direction, that is in the upward direction. So passing through the point C. So I will take here one line parallel to the link CD, and dimension or scale we have to take 8 centimeters. So I will take here line parallel to the link CD, and here I will take 8 centimeter line. So this is the radial component. So I will say from C dash to C double dash. I will show arrow also and it indicates radial component of CD. Now how to draw the tangential component? So tangential component is again in the perpendicular direction to this radial component. So here also for this link CD, this line is which indicates the velocity is in the perpendicular direction. So now currently I don't know where to extend this line. So on both sides if I extend the line, then I have to draw this line passing through the point C double dash. Now again if we observe, we don't know, this is the radial component of acceleration, this is the tangential component of acceleration for the link CD. But where is the exact location of this point D? Now if we observe at this point D there is the slider, and this slider is having motion along the vertical line. So how to show this motion in the acceleration diagram? So we know that the motion of slider or any reciprocating motion that we have to take with respect to fixed point. So we have to draw the same vertical line but passing through the fixed point, that is point O dash. So from this point O dash I will draw here one vertical line, and here the point of intersection is nothing but the point D. So now we can say that for the C double dash to D, here is the arrow towards the left hand side, and this indicates A raised to T, that is the tangential component of acceleration for CD, link CD. And from O dash to D, here the direction is vertical, and this vector O dash to D indicates that is the acceleration, or we can say acceleration of the slider D with respect to O. So I will simply say A to the base D. Now if we join the end points of this radial and tangential component of acceleration for CD, then we will get the total acceleration for this link CD. So I will join this. Then here the end point is D dash. Now we will move for the calculation part. So here first question is that linear acceleration of point D. So linear acceleration means here at D there is the slider which is having the motion along the vertical line. So for the linear acceleration of this point D or the slider at point D, we have to measure this vector O dash D dash. And it is 3 centimeters, so as per scale, which is equal to 0.15 meter per second square. Then we will move for the next question. We have to find out the angular acceleration alpha for this link CD. Now if we observe for the angular acceleration, we have to first find out what is the tangential component of CD. So here is the tangential component of CD, that is we have to measure vector C double dash to D dash, and which is 22.5 centimeters, so as per scale, which is equal to 1.125 meter per second square. So we will put this value divided by length of link CD that we have to take in meter, that is 0.45, which is equal to 2.5 rad per second. So this is the magnitude. But what about the direction? So for that we will use the compass. Now if we observe for this link CD, here in between the C point and D point, here C is the center. Now we have to show the direction. So its direction is towards the left hand side for the tangential component. So if I take the compass and this compass takes C as a center and move the compass in the direction to the tangential component. So this direction is the clockwise. So we can write here answer, that is the clockwise direction about C. So here is the answer.